Welcome to Paris number 120, and today we're talking about the effects of surface roughness on wind turbine blade performance with and without vortex generators. So up until now, we've looked at quite a few different scenarios with roughness on the surface of different airfoils, for example, and we've seen the effects of them. And generally speaking, when we have an airfoil which is in the laminar range or the transitional range, surface roughness is often very beneficial, especially at higher angles of attack. Wind turbines, though, and their blades, while they are very similar to airfoils in general, they have their own specific operation. So the effects of roughness on wind turbine blade performance is quite a unique situation. So to look at that, we're going to be looking at this paper called Estimation of Roughness Effects on Wind Turbine Blades with Vortex Generators. And this is open access, so you can find it in the link description. So let's start. So they say, as the prelude in introduction, the subject of leading-edge erosion is gaining significance in wind turbine industry in the recent years. So leading-edge erosion is any wind turbine pretty much over its entire lifespan is going to be getting like some sort of erosion on its leading edge, and that's because of rain, dust, bugs, or whatever. It often takes dents out of the blades over time, the leading edges. The combination of growth in the size of wind turbines, increased offshore installation, especially in locations with more adverse weather conditions, has made this subject crucial to the industry. Erosion of wind turbine blades is largely caused by rain, hailstones, accumulation of contaminants, which tends to change the shape of the airfoils. And the leading edge is a very important part of any airfoil. This leads to a reduction in aerodynamic performance of the affected sections. So some researchers recently presented the effects of contamination on the airfoils used at blade tips on a 5 megawatt wind turbine using CFD simulations. They reported that over the entire year, the annual energy production drops by about 3.7% just by this contamination alone. Another researcher presented a thorough review on the growing importance of leading edge erosion and different coating alternatives to reduce the impact of erosion. A wide range of drop in the annual energy production from 25% to about 3.7% is reported, and the author suggests it is due to different operating conditions and roughness levels used to evaluate the impact of erosion. The authors here also note that repair of moderate erosion can increase the annual energy production by about 2%. So while it can't alleviate that entire reduction of 3.7% or more, or 25% even, it can increase it by about a few percent. So vortex generators are commonly used to delay stall of an airfoil since they prevent early separation of the flow. And you might be thinking, what does vortex generators have to do with surface roughness? We'll get into that in a second and how they can offset each other's negative effects. But let's just stick with vortex generators for the minute. So typically they are placed on the suction side of the airfoils, usually between a core length to chord ratio of 0.2% or 0.2 to 0.3. So in other words, 20 to 30% downstream from the leading edge. And the reason why you put them here is because you usually put vortex generators just before the adverse pressure gradient occurs. And the reason why is because of the way vortex generators work. So if we have just a regular plane, it's a ground here, and we have a vortex generator, the vortex generator will start to produce a vortex. And I've covered this in other podcasts, but I'll just cover briefly here how they work. So vortex generators, what they do is they get high momentum flow from either higher up in the boundary layer or in the free stream flow, and they bring it down into like very close to the wall. What this does is it increases the velocity near the wall, so the flow is moving faster than the wall. What this allows it to do is to resist the adverse pressure gradient a little bit longer, because the adverse pressure gradient seeks to decelerate this flow near the wall. Now, if we have a fast moving flow, it just means it has to take longer for that to happen, because the deceleration is still occurring before we get to zero velocity and even negative velocity, which is when we get flow separation. So that's how vortex generators work. And the reason why we put them just ahead of where the adverse pressure gradient starts is because that's when we start to get this deceleration. We don't really want to put it any further upstream from that, because there's not really much of a benefit to it. But any further downstream, then the adverse pressure gradient is already starting to affect the boundary layer there. So we've kind of like missed out a little bit of the part that we really want to alleviate. So that's why we put them at around the 20 to 30% chord ratio, which is where the adverse pressure gradient starts. If you have an airfoil which has an average pressure gradient starting different at different positions, so let's say 10% or 50%, then you want to put the vortex generators just ahead of that. So vortex generators help delay separation by the mixing of high energy external flow with the boundary layer. Vortex generators are usually most effective at higher angles of attack, and by keeping the flow attached to the airfoil, they can delay stall and increase the maximum lift production produced. However, the drag is usually increased at low angles of attack. So let's discuss this briefly. So vortex generators, they're a big family, and you can get different sizes and different heights and different shapes. Generally speaking, they can be divided into two different sizes. One, which is the regular vortex generator, which means that they are about the same height as the boundary layer, more or less, like plus or minus 20%, let's say. Then you have micro vortex generators, and they are usually about 30% to 50% of the boundary layer height or less. And the difference is that micro vortex generators have been found to be pretty much just as effective as regular vortex generators, except they don't have the drag penalty. And the reason why they don't have the drag penalty is because the vortices that they produce are pretty much always contained inside the boundary layer. And the boundary layer is already slow moving anyway, so the pressure drag deficit that you get from a regular vortex generator is not incurred with a micro vortex generator. Now, I mentioned that near the wall, the flow is moving faster. Now, you might think, okay, well, that would usually mean that we get a higher skin friction drag because the flow is moving faster than the wall. That is true, but it's almost nothing. Like it's very small, especially considering the gains that you get from having the flow attached still and the reduction in the pressure drag. So generally speaking, the drag of a micro vortex generator, even at low angles of attack, are negligible compared to the increase that I mentioned is almost nothing compared to the regular vortex generator, which you might get like a 10-20% increase in drag, generally speaking. So that's what they mean here. So in this paper, they explore different methods to model the effects of surface roughness in RAN simulations and investigate the performance of a vortex generator in rough conditions. Due to the leading edge erosion, the nature of the turbulent boundary layer changes. This is additional dissipation near the roughness elements, which leads to the thickening of the boundary layer. The loss in momentum makes the boundary layer prone to early separation. However, the vortex generators add momentum to the boundary layer by mixing external flow, thus, in principle, overcoming the negative effects of leading edge erosion. For the final application, the DU97W300 airfoil is used. So this is a very common wind turbine airfoil, and it was designed by Delft University, I think. So let's get into the numerical method. We mentioned here that they're going to try to figure out a way to model surface roughness in RANs. And this is quite difficult to do. So you can either like have different equations doing it or actually have the surface rough. We'll talk about how they're doing it here. They're using different equations to like model the roughness. They say in this study, they aim to model the impact of roughness by qualitatively mimicking the behavior of the flow around these roughness elements. In order to motivate the roughness model used in the present study, a brief introduction of turbulent boundary layers and how roughness impacts the boundary layer is presented below. So the turbulent boundary layer can be broadly divided into two regions. The inner region, where viscous dissipation is comparable to that of the turbulent dissipation, and the outer region, where turbulent dissipation is dominant. In the inner region, so closer to the wall, the inner region can be further subdivided into three regions. The viscous sublayer, where viscous effects dominate and turbulent effects are absent, a buffer region, where the turbulent stresses start to grow, and finally an overlap region or a logarithmic overlap region, where the turbulent and viscous dissipations match. The overlap regions lead into the outer boundary layer, and the viscous effects here are minimal. So this is a very interesting point here. I just mentioned a few different points in the boundary layer. So we have this viscous sublayer. And in other podcasts, when I've talked about CFD, I've talked about the Y plus value. And this is effectively how well resolved the flow near the wall is. And the Y plus value you typically want to have below 1. And there are some turbulence models, for example, the K epsilon model, where you can go 30 or more, and they say that it's okay, but the K epsilon model is rubbish anyway, so it's not really much of an issue either way. But for regular turbulence models that are actually good, you want to have a Y plus value of 1 or at most 5 or less. And the reason why is because the subviscous boundary layer is in this region. So if you have a Y plus value of 1, that means you're actually now modeling the subviscous boundary layer much better, and that means you're going to get a more accurate result. If you don't have a Y plus of 1, let's say a Y plus of 20 or 30, then you're outside the subviscous boundary layer. And this subviscous boundary layer is very important for the development of the boundary layer. So that's why we want to get such a resolved boundary layer grid near the wall. So they say here, the regions of the boundary layer between a Y plus of 5 and 30 is the buffer region, and below 5 is the subviscous boundary layer. So that's just some theory behind the CFD, why we want Y pluses to be so low and what they correspond to in terms of the boundary layer. So the presence of surface roughness on the wall alters the nature of the velocity distribution near the wall. The roughness elements will introduce new turbulent fluctuations in the flow, increasing the skin friction, among other things. So we mentioned that briefly. Typically, a standardized notion of roughness known as the equivalent sand grain roughness height, so KS, is used to denote roughness of a wall. A given physical roughness distribution is converted into the equivalent sand grain roughness height using empirical correlations based on the stretched roughness height KS plus, which equals the equivalent sand grain height times the wall friction velocity divided by the dynamic viscosity, can be calculated in the 3 different regimes. So if this value of KS plus, which is just a value that we calculate to determine how smooth or rough the wall is, if this value KS plus is below 5, we can term the wall as hydraulically smooth, which means that it's just smooth based on fluid mechanics. If this KS plus value is between 5 and 70, we call it transitionally rough. And finally, if the KS plus value is greater than 70, we say that the wall is fully rough. If the roughness elements are within the subviscous boundary layer, so KS plus is less than 5, the effects of roughness is not relevant and there is no difference between the smooth velocity profiles. So that's pretty amazing. If the roughness is so small that it's only in the subviscous boundary layer, it doesn't really affect the subviscous boundary layer that much, and it doesn't affect the boundary layer in general, so we can ignore it. As the height of the roughness elements increases to above 5 and below 70, a shift in the velocity profile is observed. Once the roughness elements are fully within the overlapped region of KS plus is greater than 70, the viscous sub-boundary layer plays no part and the flow is in the fully rough regime. So that's quite an interesting theory there about the roughness and the effects of roughness on the wall. So let's talk about the turbulent flow over a 2D flat plate. What they do in this paper, which is really nice, is they start to build up their simulation. They start off with a 2D flat plate, then they go to an airfoil, and then they go to a wind turbine blade. So, and they validate the process at each step just to make sure that they're doing it properly. And it's very well done here. So let's cover the effects of surface roughness over a 2D flat plate in here and in CFD. So turbulent flow over a flat plate with different roughnesses are simulated with both the Spallard-Almaras and the SST turbulence models. They looked at both of these turbulence models to see which one is better. And the results are a little bit surprising, I guess. They say the velocity profiles for different roughnesses are presented in Figure 1. The plate at the plate domain is 2 meters long and it's a Reynolds number of 6 million. So pretty much it's going to be turbulent. A minimum Y plus value of 0.4 is maintained on the flat plate. So that's quite nice. From Figure 1, we can see that the clean case matches the viscous sublayer and the log law in the overlap region closely for both the Spallard-Almaras and SST models. So that means that in this region, both these turbulence models are accurate. Furthermore, increasing equivalent roughness heights has the predicted effect of shifting the velocity profile away from the clean case. So no surface roughness. And once the surface roughness is above 70, that KS plus value I mentioned, the viscous sublayer disappears. To further verify the two results, a comparison is made with the theoretical shift in velocity profiles as proposed by a researcher. Comparisons to theoretical predictions of the velocity shift in Figure 1 show a slight overprediction in the observed transition roughness region by the Spallard-Almaras model. So that means that the Spallard-Almaras turbulence model may not be that good for this purpose, but they say this was also reported by some other researchers, and the SST model, this roughness model, does not perform nearly as well as the Spallard-Almaras model, especially in the full rough regime. So this means that both the turbulence models that they wanted to use, neither predicted the boundary layer very well, like 100%, but the Spallard-Almaras model is better than the SST model in this particular case. And that's quite surprising because the SST model is usually better than the Spallard-Almaras. And we'll get into in a little bit how it is better and in certain situations. But in this particular case, the Spallard-Almaras model was better. So they say, additionally, due to the other limitations in the KMB SST roughness model reported elsewhere, the roughness, they're going to go with the Spallard-Almaras model. They say the roughness heights due to leading edge erosion is likely to span all the regimes of roughness at various stages of erosion. And in order to ensure that even fully rough cases can be adequately modeled, they want to use the Spallard-Almaras model. So they say it should be noted that various corrections for this SST roughness model have been proposed, but are not investigated in this current study. So in other words, there are a lot of researchers working on how to actually model surface roughness, and nothing is working 100% well at the moment. But SST and Spell-Delmara seem to be the two hopeful ones, and there are corrections for the SST model, which they haven't done here. So they're using Spell-Delmara instead. It's just easier for them at the moment. So in figure 2, this is just an interesting part that I wanted to cover as well. It shows the comparison of the skin friction coefficient from SST and Spell-Delmara's roughness models compared to experimental data. Now, one thing that they show is that the rough Spell-Delmara's model is significantly better in terms of its prediction in the experimental data than the SST or the clean versions. So this is just another thing showing that the Spell-Delmara's turbulence model is, in the rough situation, is better in this particular case than the SST model. So they've looked into the flat plate and the effects of this turbulence modeling on this flat plate performance. Now they're going to be looking at an airfoil. So they're going to be looking at a NACA 65215 airfoil validation. So the Spell-Delmara model is further validated against this airfoil, and the Reynolds number is 2.6 million, and the roughness covers the entire upper surface, and on the lower surface, it begins at the leading edge and goes up to 15% of the chord. So what does this all mean? So the Reynolds number is already very high. 2.6 million means that the flow over the airfoil will become turbulent at some point. Generally speaking, it should probably be about 30%, 25% of the airfoil from the leading edge. The surface roughness is completely covering the upper surface, and the lower surface has just the leading edge part has some surface roughness. So they say in table 1, a two-dimensional C-grid topology is used for all simulations. A grid refinement study is carried out at an angle of attack of 8 degrees with meshes of 150, 250, and 450 nodes on the airfoil surface. A Y plus value of less than 1 is maintained for all 3 grids. The resulting lift and drag coefficients are listed in table 1. Based on the results in table 1, the grid with 250 points on the airfoil is used for further computations. And I point this out because in the last podcast that we did, or I guess 2 podcasts ago, in 118, we looked at some CFD and some validation and some grid independent studies. And the grid independent study that they did was actually quite flawed in that they looked at 3 different grid resolutions, and they found that as they increased the grid resolution, the lift and drag values were still changing, but they just went, okay, well, it's validated, and we're going to go with the most refined grid. That's not how you do grid refinement studies. This is how you do grid refinement studies in this paper. So what they did is they have 3 different grid refinements, 150 nodes, 50 nodes, and 450 nodes. They looked at the lift and drag coefficients, and then they looked at how much they changed. And then they went, okay, well, the 50 node one, which is the intermediate resolution, isn't really that different to the very fine resolution. So that means we can still go for the 50 grid resolution and be fine. This is how you do grid resolution studies properly. If you were to get here and you went to 450 nodes and you found that, okay, it's still changing in lift and drag a lot compared to the intermediate mesh, you then need to go to an even finer mesh to see how it changes again, and then finally get to the point where it's not really changing that much, and then go for the second most refined grid. So I like how they've done this here. So they say based on the results in table 1, they're going to use the intermediate mesh of 50 grid points. The far field and wall boundary conditions are applied at the edge of the domain and on the airfoil respectively. The left figure 3 shows the comparison of numerical results of the Spell-Delmara model under clean conditions, and with a roughness height of the equivalent sand grain roughness compared to the chord of 1.23 by 10 to the minus 3. So it's very, very fine. The numerical results from the CFD compare very well against the data from another researcher at lower angles of attack. But when they get to high angles of attack, their CFD overpredicts the maximum lift. This could be due to the later prediction of the flow separation by the Spell-Delmara turbulence model compared to the experiments. And this is one problem of Spell-Delmara. It has only been developed to predict the airfoil performance at low angles of attack when the flow is completely attached. Once you start getting to the stall angles of attack, the Spell-Delmara turbulence model starts to break down. That's where the SST, K-Omega, or other turbulence models come into their prime. So they say since no experimental pressure data is available, it cannot be confirmed that the Spell-Delmara model breaks down because it underpredicts the flow separation. but it is likely still, because that's typically where it falls short. The addition of roughness causes a reduction in the maximum lift of 28.8%. So that's quite a lot. And you might think, well, why is that? So surface roughness really is only good when we have a laminar flow to begin with. The reason why is because it turbulates the flow. And by doing that, you can then delay stall. So if you're at high angles of attack and at low Reynolds numbers, that's where surface roughness really plays a very important role. If you're at low angles of attack and or at high Reynolds numbers, then surface roughness is not very good. It's actually just increasing the turbulence and increasing the drag as well, which is what they found here too. It increases the drag, it reduces the lift. So they say on the right of figure 3, the predicted lift coefficients with different roughness heights are shown, and they say with increasing roughness, the maximum lift value and the angle of attack at which this occurs decreases. So surface roughness is bad for airfoil performance at high angles of attack and at high Reynolds numbers. So based on the computer skin friction drag at an angle of attack of 8 degrees, the Ks plus varies from 70 to about 850. These values suggest the flow is likely to be fully rough, but it will vary depending on the flow conditions. Due to some of the deficiencies observed with the SST roughness model, the larger Ks plus values previously, only the SA Dispel-Dalmaris model is used in this work. Now that's debatable. I mean, the SA Dispel-Dalmaris model definitely breaks down at high angle attack, but at low angle attack it performed quite well, so it really depends on what you want to do. So they've looked at the airfoil and they've found that in some situations it performs very well there, the CFD, in other situations not so much. Let's look at the effects of roughness on turbine blade sections. So a typical wind turbine airfoil, the DU-97-300, which is the Delft designed airfoil for wind turbines, is chosen to test the effects of roughness and verify if vortex generators can alleviate the anticipated drop in performance. This choice is motivated by the availability of experimental data for clean and vortex generator cases. The simulations are carried out at a Reynolds number of 2 million for both clean and vortex generated cases. For both clean and vortex generated cases, a 3D mesh is generated where the airfoil is extruded to the span wise direction, and a body fitted mesh is generated around the vortex generator. So what does this mean? It just means that they've got their airfoil, their DU-97-300, and I'll draw this actually. Let's say you're looking at it from the top. They have their airfoil at the top, and they've cut it in half. They've got one vortex generator coming along here. Then on this surface, they've done a symmetry plane here. And then they've just put a mesh around this entire airfoil, and they've got a boundary layer forming. That's what they mean here. So a symmetry boundary condition is used on the span-wise extrusion boundaries, and the following cases are considered. So an airfoil with no roughness or vortex generators under fully turbulent conditions. This is denoted as clean. The second condition is airfoils with vortex generators under fully turbulent conditions, so no roughness, but just airfoils. The third condition is no vortex generators, but roughness. And then finally, the fourth case is vortex generators and roughness. The reason why they looked at these four cases is they want to see if the vortex generators can alleviate the problems that surface roughness incur, which is the reduction in the lift and increasing in drag. So they say the vortex generators are placed at 20% of the chord from the leading edge of the airfoil. And as I mentioned earlier, this is where you really want to have it. Since the symmetry plane boundary condition is used on the extrusion boundaries, the geometry represents a row of counter-rotating vortex generators as shown in the right of figure 4. So they only model one vortex generator, but because they have a symmetry plane, this is effectively two vortex generators now in counter-rotating situations. So let's look at the vortex generator drag polars. So figure 7, you can see that the additional vortex generators have delayed the stall until an angle of attack of 18 degrees as expected. When it's just clean, the stall angle of attack was like 12 degrees. So vortex generators are incredibly good at delaying stall, as we know. A very close match is observed at lower angles of attack, but deviations increase at high angles of attack compared to the experimental data. And again, this is often where CFD does break down when stall occurs. As for the drag coefficient, as you'd expect at high angles of attack with vortex generators, the drag coefficient is usually better. It's lower because the flow hasn't separated, so we don't have that pressure drag increase. But once the flow does separate, then we do get that drag penalty again. It's just it's delayed. So what about the effects of roughness? So determination of the appropriate values of the roughness height K is difficult due to the lack of experimental data for the airfoil under consideration in rough conditions. Additionally, since no transitional model is used in this study, the roughness height used must ideally trigger a very early onset of transition to ensure the flow remains turbulent over the airfoil. Several studies on isolated 3D roughness elements have reported a critical Reynolds number of 600 based on the roughness height K, which induce larger instabilities in the flow that trigger transition at the location of roughness or even upstream. What does this all mean? So what they're saying is in their CFD, they're not really looking at transition. They're just assuming that the entire flow is turbulent. So what they need to do is select a surface roughness, which ensures that that does occur. So if you were to have a very low surface roughness, well, in real life, the airfoil will not be under turbulent flow completely. So if you were to do your CFD, assuming that it is turbulent flow, then you're obviously going to get a wrong answer. So what they want is they want to have a surface roughness which is so large that it will be result in a turbulent boundary layer very close to the leading edge, if not the entire airfoil. So what they've found is if you have a Reynolds number based on the surface roughness height of 600 or more, then you'll get turbulent boundary layers forming from the pretty much the leading edge of the airfoil. So that's what they're looking at doing. They say in this paper, they use a value of surface roughness height to ensure that the Reynolds number based on this surface roughness height is 800, so even higher than 600. Once the roughness height K is defined, an equivalent sand grain roughness height, Ks, must be estimated. In order to mimic leading edge erosion, the airfoil surface roughness from the leading edge of 13% from leading edge or on the pressure side, and from the leading edge to 2% on the suction side is assumed to be rough. So figure 8 shows the lift and drag plots of the fully turbulent case of the Reynolds number under 2 million. And what we find here is that we have the clean case, which performs sort of moderately well, but the airfoil, just with vortex generators, performs the best. And then when you put in surface roughness, it always degrades the performance, even with vortex generators. Interestingly, when you have vortex generators and surface roughness, you can get better performance than just the clean case. But if you have no vortex generators and just rough, then the airfoil performs worse. So overall, it means that the vortex generators can overcome the deficit that the surface roughness introduces and more. So despite a fairly moderate choice of roughness height, the flow is already in the fully rough regime. Additionally, the airfoil appears to stall slightly earlier due to the presence of roughness. Adding a vortex generator on the rough airfoil appears to counteract some of the negative effects of the roughness by increasing the lift. However, the drag also increases. That's to be expected. If they use micro vortex generators, I'm not sure how that would go. I reckon it would be better because you wouldn't get that increase in the drag, but I think it would still have just as good an effect on delaying stall. So that's something to look into. They say the vortex generators do delay the stall, and therefore now stalls at 15 degrees, even with a leading edge roughness compared to like 12 degrees for the clean case. A clearer picture emerges when they consider the pressure coefficients in different cases. So figure 9. At an angle attack of 12 degrees, the fully turbulent clean flow is separated close to the trailing edge at around 90% from the leading edge. So the last 10% of the airfoil has separated. This angle of attack also corresponds to the maximum lift coefficient. Under rough conditions, the flow separates much earlier. However, the vortex generators help the flow to remain attached throughout. The difference is clear when examining the pressure coefficient at an angle attack of 15 degrees in figure 9. Under both clean and rough conditions, the airfoil is under stall. Flow remains attached longer with the vortex generator cases compared to the clean and rough conditions, but it still separates at some point. It's not 100% attached, which you might need to get more vortex generators or more efficient vortex generators to do that. So what about the aerodynamic efficiency? So comparing the clean and vortex generator cases, the efficiency at lower angles is lower with vortex generators due to the additional drag, but at high angles of attack beyond stall, as you'd expect, the efficiency with vortex generators remains high as expected. And this is because lift is still being produced and drag is still fairly low compared to the clean case and the rough case without vortex generators. On the right of this figure 10, the comparison of efficiencies with roughness is shown. Due to roughness, a reduction in efficiency is observed both with and without vortex generators as expected. The maximum efficiency is also reduced in both cases. At higher angles of attack, the vortex generators increase the efficiency even under rough conditions, but it's still not as good as just having no roughness at all. So, in conclusion, let's talk about the power analysis. I'm getting ahead of myself here. So, a preliminary analysis of the effects of the roughness on a wind turbine blade at an incoming wind velocity of 10 meters per second is performed using blade element momentum theory. With a rough case, a drop of 2.5% is observed compared to the clean case. The addition of vortex generators, however, do not appreciably change the power output when compared to the rough surface. This is likely because the operating angle of attack for this airfoil is in the linear region where the vortex generators do not have a beneficial effect on the aerodynamic performance. So in other words, roughness has a detrimental performance on blade profiles across all angles of attack, whereas vortex generators only have a positive effect at high angles of attack, and at low angles of attack, they don't really have much of an effect or even a slightly negative effect due to higher drag. So blades like wind turbines, they operate in the pre-stall angle of attack range, and that's not really where vortex generators are supposed to operate. Like they're not really designed to benefit an airfoil at this range. So the benefits that you do get are not surprisingly not doing anything for the airfoil at this range. If you go to high angles of attack, then you would get much better power output, but that's not where most wind turbines operate. So in conclusion, it means that vortex generators are not really, it's like a moot point just to put vortex generators on a wind turbine to overcome the negative effects of surface roughness, because you're not going to be operating the wind turbine at the conditions that the vortex generators are designed for anyway. So finally, it is clear that surface degradation leads to reduction in aerodynamic performance as the flow tends to separate earlier, which can even lead to premature stall. A reduction of 2.5% in power production is observed under rough conditions compared to clean cases. The addition of vortex generators appears to counteract the negative effects and roughness when the angles of attack are very high. However, due to the presence of vortex generators, drag increases further under rough conditions and at low angles of attack. The addition of vortex generators did not appreciably change the power produced by the rotor compared to the rough surface, where the polar drag data that are used for the power analysis are synthesized. So, I guess we can just conclude that surface roughness bad, vortex generators good, and putting both together, they're kind of okay. So that's that in a nutshell. So that's it in this podcast. Make sure to like, subscribe, and if you want to get better at theory and or CFD, like we've gone through here, check out courses in the link description. And if you want to make your experimental data 2 to 4% more accurate, check out Aerodyne Hawk. It actually measures the density of air during your experiments, which is very important because the density of air changes every day. So like if you turn up to work at 9 a.m., you do your experiments then you come back after lunch and do some more experiments, the density of air is probably changed by 2 or 4%, maybe more even. So that means you have that error in your data. And when you go to CFD and you try to validate your CFD data, well, you could have an error there, and that's going to make your CFD validation much more difficult because your CFD is running on a wrong or a different air density, and that creates problems. The Atmosphere Hawk is an instrument we make which gets rid of that problem for you, and it makes your experiments much more accurate, and it's really something that you need to be measuring. Otherwise, you can't really trust your results very much unless you have like really big differences, which unfortunately we don't get these days. Most differences that we get are like in the range of like 1, 2, 3%, which is exactly where this density of air changes. So check that out. Link in the description, and I'll see you next podcast. Peace, amigos.